So this is part 3 of homework 5, and we will be deriving the expression for heat transfer rate Q in terms of the overall heat transfer coefficient U, area available for heat exchange A, and the log mean temperature difference for a co-current heat exchanger, and explain why this is also valid for a counter-current heat exchanger. So as you can see up here on the board, I have a few diagrams of this situation that we have. So as you can see here, the hot is transferring some amount of heat in a specific area to the cold. It's not the cold transferring to the hot. We gotta remember it's hot transferring to the cold. And then as you can see over here, they keep transferring until they reach a certain point or temperature in which they will stop transferring that heat. And I have two equations here for the heat transfer. So it says that the change in heat is equal to the mass flow rate for the hot end times the heat transfer times the change in temperature on the hot end is equal to the negative of the current of the hot end times the change of temperature in the hot end. And then it's the same here for the cold end, except it won't be negative because, again, the hot is transferring to the cold, not the other way around. So now, as you can see over here, we can have the problem in terms of that heat transfer coefficient U that it says here. So we have that the change in heat is equal to that heat transfer coefficient U times the change in temperature times, I'm going to switch this to capital. Makes me think of time when I have it lowercase there. Make sure this is capital, there we go. Times the differential area. Then we can rewrite that as d delta t is equal to the change in the temperature of the hot end minus the change in the temperature in the cold end. So now, using these equations that I have just laid out, we can start with an equation of d, or the difference in the change of temperatures, is equal to our heat transfer times 1 over CH minus 1 over CC. And then now we can plug in for our heat transfer this equation up here. And then we'll end up with d delta t over delta t equal to u, and then this whole thing again dA. So now what we can do is take the integral from point 1 to 2, and we'll end up getting natural log of T2 over T1 delta T2 over delta T1, and then is equal to U A 1 over CH minus 1 over Cc. So now we can use these heat transfer equations from before for our Q. So we know that Q is equal to CH and then times our change in temperature here, which we can just write as T HI minus T H0, and then the same for the cold. So CC T CI minus T C0. And then now what we can do is plug these in here, and we will end up getting ln, the same over here, ln delta T2, delta T1 is equal to, and then we'll have U A over Q and then T HI minus T H0. And then these should be plus signs actually, because this should be a plus in between these two. So plus, and then we have our T CI minus T C0. Like that. And now what we can do is actually rearrange these. So I'm going to copy this down again. Then we'll have T HI minus T CI, and then plus T H0 minus T C0. And then now we can actually represent these by our, over here, this will be delta T1 and delta T2. So there was a little mistake here. Obviously, since we flipped these, this will actually become a subtraction sign. And then now what we can do is get it in terms of Q. So Q will equal, we'll have U A, and then our delta T1 minus delta T2 all over ln delta T2 over delta T1. And basically we can simplify this. So we'll have UA, and the log mean temperature, or actually it'll be the difference of the log mean temperature. And this will be our final equation that the problem is asking for. And then also it did say that we were to explain why this is also valid for a countercurrent heat exchanger. And basically what that means is if you changed it from the cold going to the hot, and basically then you would change your initial temperature and final temperature, and eventually if you did all this driving out again, you would actually end up at this same derived expression.